Welcome back to another Explainer. Today, we're diving into something that literally sounds like pure science fiction, but it's actually incredible, real-world nuclear physics. We are talking about fast breeder reactors. It is, quite frankly, the absolute alchemy of nuclear power. Okay, I want you to imagine something for just a second. What if a machine could actually create its own fuel right as it runs? I know, it sounds totally impossible, right? Like it's defying the laws of thermodynamics or something. But in the world of nuclear energy, the breeder reactor isn't just this fascinating machine. It's really a seemingly magical solution to a massive, massive resource problem that nature just kind of handed to us. So let's dive into our roadmap for this explainer. First step, the nuclear fuel problem. Then, fast reactors explained. Third, fissile versus fertile. Fourth, the alchemy of breeding. And finally, we'll wrap up with the ultimate power potential. All right, part one. The nuclear fuel problem. Specifically, we're looking at scarce fuel versus abundant rock. So here's the core dilemma that nature gave us. We have very, very little usable fuel naturally available to us, and just a whole lot of essentially useless rock. To really grasp this, think about how standard thermal reactors operate. They consume uranium-235 as fuel, right? But nature only gave us a tiny, tiny fraction of this fissile, or, burnable material. It's incredibly scarce. Meanwhile, these standard reactors just leave massive amounts of uranium-238 and thorium-232 sitting around completely unused. I mean, they are super abundant, but neither of them can actually sustain a chain reaction on their own. So, straight out of the ground, they're virtually useless as direct fuel. To put that into perspective, natural thorium-232 actually has 100% abundance. It's available in even larger quantities in the Earth's crust than uranium is. But despite literally being everywhere, it's almost worse than uranium because it has absolutely no naturally fissile isotope. Out of the ground, it really is just abundant rock. Moving on to part two, fast reactors explained. High energy, high requirements. Now, this specific reactor technology is our very first step to solving that massive scarcity problem. But, it comes with a catch. A fast reactor actually has no moderator. So instead of slowing things down like your traditional thermal reactor does, it just lets neutrons fly around at extremely high energies. We're talking around 100 kilo-electron volts. Essentially, these neutrons are moving with just absolutely incredible speed and power. Let's break those specs down a bit. Because there's no moderator, and most of these neutrons are just zooming around at 100 keV, about 90% of the fissile absorption occurs well above 10 keV. Now, while this high-energy environment is incredibly powerful, it actually presents an immediate economic problem. It requires a substantially large proportion of fissile atoms just to get the reaction started in the first place, meaning you need huge, huge enrichment compared to a standard thermal reactor. And since we already established that our fissile material is incredibly scarce, well, this initially seems totally uneconomical, right? That brings us to part three, fissile versus fertile, unlocking hidden potential. Okay, this is where things get really cool, and we shift from the problem of super expensive enrichment to the absolute secret weapon of the fast reactor. We need to define a really critical term here, fertile material. These are isotopes, like our superabundant uranium-238 and thorium-232, that on their own cannot sustain a chain reaction. But because they are fertile, they hold this hidden potential to be transformed into brand new fissile nuclides. So the crucial point here, the real game changer, is that a breeder reactor completely leverages this fertile material concept. It doesn't just burn up our scarce natural fuel. No, it is essentially an alchemy machine. It efficiently converts that abundant, otherwise totally useless rock into highly valuable combustible nuclear fuel right there inside the reactor. Let's look closer at this in part four, the alchemy of breeding, step-by-step transformation. Let's look at the actual mathematical physics of how this transformation happens. There are exact conversion paths for both uranium-238 and thorium-232. And hey, if the equations for these paths look a little dense right now, don't worry at all. We are going to break these complex pathways down super simply right now. Let's just trace the uranium breeding chain chronologically. It all starts with a simple capture. Our fertile uranium-238 atom captures a stray neutron, and it becomes uranium-239. Now, this new isotope is unstable, so within about 24 minutes or so, it undergoes a beta decay, transforming into neptunium-239. Then, over the next 2.3 days, it undergoes yet another beta decay. And the final result of all this? Plutonium-239. Just like that, boom, we've successfully bred brand new fuel. To summarize these two amazing conversion paths side by side, our fertile starting material, uranium-238, is bred directly into plutonium-239. And if we were to start with thorium-232 instead, it follows a really similar path through protactinium to eventually become uranium-233. We have successfully created what the literature officially calls artificial or man-made fissile materials. Both plutonium-239 and uranium-233 are now fissile and completely ready to generate power. Which brings us to our final section, Part 5, the ultimate power potential. Why fast reactors win. Okay, so this is really the climax of our entire scarcity problem. The absolute magic of plutonium-239 is that when you use it in a fast reactor, it doesn't just burn and produce energy. Actually, it produces a significantly larger number of neutrons than it ever would in a standard slow reactor. And that massive surplus of neutrons, that's literally the key to making this whole system work. Think about it. Because we have so many extra neutrons just flying around in there, way more neutrons are made available to be captured by the uranium-238. This leads to a massive, substantial conversion of our superabundant uranium into even more plutonium-239. So instead of getting hardly any fission energy out of uranium-238, like we do in a slow reactor, the fast reactor extracts a huge amount of power from it through this continuous conversion cycle. This incredible fissile breeding potential completely offsets those initially uneconomical, high enrichment needs that we talked about earlier. It literally turns a scarce resource problem into an incredibly abundant energy solution. Which leaves us with one final pretty provocative puzzle pulled straight from our source text self-assessment questions. We know that plutonium-239 decays to uranium-235 by alpha decay, right? So think about this for a second. Will this not actively replenish the very scarce uranium-235 fuel that we started out lacking in the first place? It's such a brilliant question about the beautiful cyclical nature of these isotopes. I want you to ponder that as you review these concepts, and definitely keep exploring the incredible alchemy of nuclear power. Thanks so much for joining me on this explainer. Stay curious, and I will catch you next time.